So these examples here are all the same type, right? So these 4 examples was when we talked about writing linear equations. So when you write a linear equation, there was 3 cases, right? So case 1 is when they gave you the slope and a point. Case 2, they gave you 2 points. Case 3, they gave you a linear equation and a point. So for all these situations, we use the formula y minus y sub 1 equals m times x minus x sub 1, right? This is the point slope form. Remember here, you can plug in your point, and in all these situations, you're always given at least 1 point. So that point can get plugged into right here, right? You can plug it in there. And only in case 1, you're given the slope right away. So you can just plug it in right into your equation, and that's it. Now in the other 2 cases, you need to try to get your slope, right? So in case 2, you have to use the slope formula, which is like where the difference quotient comes from. So the slope formula helps you use the 2 points to find your slope, right? Which we use this a few times to find the slope between 2 points. And then a linear equation, remember, if you write your equation in slope-intercept form, right, so whichever format the equation is in, if you isolate your y value, your slope is the coefficient of x. So in all those scenarios, you will plug in a slope, and you'll plug in your point, and you'll find your equation. The only times I said that you're not going to use these two, this equation, is when you talk about a horizontal line. Sorry, my pencil disconnected. When you talk about a horizontal line or a vertical line. Because the equation of all horizontal lines is when y is equal to a constant, right? The equation of all vertical lines is when x is equal to a constant. That's kind of how we got the vertical lines, like the vertical asymptotes for the rational function, right? Because we said the values of x that make your denominator 0 are some numbers, and when x is equal to a number, it makes a vertical line. Hence, we have those vertical asymptotes. And remember, the slope of all horizontal lines is 0, and the slope of all vertical lines is undefined. All right, we're just talking about the linear equation itself. So that means whenever you're dealing with a horizontal line, you're just looking for what y is, which in each one of these situations, you're given a point. And the point's going to have an x and y. So for a horizontal line, you're just looking for the y. For a vertical line, you're just looking for the x. So the point will already give that to you. Again, how do you know you're dealing with a horizontal or vertical line? Well, if you come across one of these 2 slopes, or if it directly tells you horizontal or vertical, or if you recognize that right? In this situation, if both of your y values are the same, you're probably dealing with a horizontal line. If both of the x values in both of these points are the same, then you know you're dealing with a vertical line. Or in this situation, the linear equation that's given might be a horizontal line or it might be a vertical line, right? So let's go through these. That was just a quick overview of what we do here, because write the equation of a line passing through the point, this one and this one. So that means we're dealing with case 2. They're giving us 2 points, and we're going to write the equation in slope-intercept form and then graph it using slope-intercept form. So one thing to remember is you want to make sure that you're subtracting in the appropriate order. What does that mean? If you notice, this x and y are from the same ordered pair. This x and y are from the same ordered pair. So when I go and find my slope from these 2 points, I write, so I have to find this is x, that's y. This is x, that's y. Again, but they're from different points, of course. You can either label them or just know that you are, for your y, is -1, and then your x is 2. Because I'm choosing from the same ordered pair. Look, these 2 are from the same ordered pair. These 2 are from the same ordered pair, and directly above each other. So this is my y, that's my x. And then we subtract in that same fashion. But when I subtract this y, you want to be careful because that y has a negative. And this negative comes from the formula. So don't just think, oh, there's already a negative there. I don't need to write the negative from this ordered pair. No, you have to include that negative as well. And then the x right under it, which is 4. Because those 2 negatives are going to become positive. 2 minus 4 is -2. -1 plus 2 is 1. Divided by -2 is just going to be -1/2. So I have my slope. And remember, we use this point slope formula. Y minus y sub 1 equals m times x minus x sub 1. And if you're asking, well, what point do I use? Remember, the line that we're looking for passes through both of these 2 points. So if it passes through both of them, either one of them is perfectly okay to use in my formula. So let's say if we go with the first one, it's going to be y minus, and once again, that y value is negative. So you have to make sure you incorporate that negative. This negative comes from the formula. This negative comes from the ordered pair. And then my slope is -1/2 x minus my 2. Now don't choose a y here and then x from the other one, because that will really throw the problem off. Now those 2 negatives become positive. I distribute here, it's -1/2 x. A negative times a negative is positive. And 1/2 times 2 is 1. I subtract 1 to both sides. The 1's cancel, and I'm left with y is equal to -1/2 x. Now, to graph this, I can just plot these 2 points and draw the line and graph it, right? Technically, that would be the graph of it. Or I can look here and I know my slope, because once your y is isolated, you're in this slope-intercept form. Remember what I said? If it's in slope-intercept form, the coefficient of x is your slope. So here, the coefficient of x is my slope. Now, the constant here is my y-intercept, but I don't have a constant. So we have to assume that constant is 0. So it means my y-intercept is, well, remember for y-intercept, it's an ordered pair where the x is 0 and then whatever constant you have here is your y value. But since we don't have one there, we assume it is 0. Think about it like saying plus 0. So that means our y-intercept is at the origin, right here. And our slope is negative 1/2. And don't forget, I said when you're graphing it this way, you can either give the negative to the numerator or you can give the negative to the denominator. So negative 1 over positive 2 or 1 over negative 2. But what you cannot do is give the negative to both of them, because then that would make a positive slope versus a negative slope. So either way, if you go down 1 and right 2, that's the same thing as, right? So you can do this one, which is down 1, right 2, or you can go up 1 and left 2. But they both give you for the same direction. Oops. And we sketch the graph. They both give you the same line, right? Regardless if you give the negative to the numerator or the denominator, right? And this, remember how we said this is sort of that visual representation of a negative divided by a positive, you still get a negative, right? A positive divided by a negative, you still get a negative, right? It's like a visual way of seeing that. Still a negative slope. Now, next one is really nice because it gives me my point and it gives me my slope. So it looks like case 1 where they give you your slope and the point. And you can do it that way and it's perfectly fine. Or if you do notice something, remember what I just said, that the slope of all horizontal lines is 0. So instead, if I wanted to do this problem a little quicker, because I know the slope is 0, there should be a little like light bulb going off saying, wait, I remember something about a slope of 0. The slope of 0 is a horizontal line, and the equation of all horizontal lines is y equals a constant. So that means I'm just using the y value. So my answer is just 2 over 7, right? If this would have said undefined, then I would know, oh, I'm dealing with a vertical line, and I would choose the x value, right? If there was any other number, well, then I have to just resort to using the point slope form. And I can still use the point slope form even now. I can just plug in 0, plug in the 2 points, and I'll get the exact same answer. But if this said undefined, you definitely cannot use this because you can't plug in undefined and distribute the word undefined in the problem, right? But that's where you remember these two ideas, that the slope of all horizontal lines is 0, the slope of all vertical lines is undefined, right? And that happens in various ways. Either you're told, you recognize it, or if you're calculating the slope formula, right? If you get 0 in your denominator, that's undefined. But the only way to get 0 in your denominator if these two numbers are the same. So, something to keep in mind. Now this next question is case 3, where if you notice they're giving us a linear equation and a point. And I'll highlight them. Here's the point. Here's the linear equation. Now, but there is some additional things when we talked about the idea of being perpendicular, right? So what does it mean to be perpendicular? That means the slopes. So let me put it here. There's two things to be perpendicular to a line. The slopes are reciprocal of each other. and the slopes have opposite signs. Now, if it had said parallel, two things also. You have the same slope, but you have a different y-intercept. But in both of these situations, to determine the slope, remember you need your slope-intercept form. So that means I'm going to take this line and I'm going to try to isolate my y value. And I do that by subtracting x to both sides. That leaves me with 3y is equal to, now remember, slope-intercept form is y equals mx plus b. So for the sake of keeping this format, I'm going to write negative x plus 6. And it's a good reminder that the commutative property of addition does exist, right? Where you can always change the order of terms as long as the sign stays with that term, right? You want to make sure you keep them together. And then you divide everything by 3 on both sides. And remember the rule, if you have one term in your denominator, you can always split it into 2 if you have multiple terms in the numerator, which would be negative x over 3 plus 6 over 3. Now, for either one of these, I really only care about the slope. The different y-intercept, that kind of happens on its own. I don't actively change anything. I'm really just focused on the slope, right? Because the formula itself cares about a point and a slope. Hence why it's called point-slope form. So I'm really only focused on the slope of this line. So here, it's tricky because I only see it's dividing by 3. But technically, there's this negative 1 there as well. So my slope from this line is negative 1/3. But I want to be perpendicular to this line. So this is the symbol for being perpendicular. It's kind of upside down capital T. So the perpendicular slope is, remember I said, the signs are opposite. So that means this one is going to turn from negative to positive. And then you do the reciprocal of the fraction. So 1 over 3 becomes 3 over 1, which is just 3. Right? We normally just write 3. We don't write plus 3 over 1. We'll just write 3 as our slope. If this question had asked, I want the slopes to be parallel to each other, I would just write the exact same one. But I always do like to separate it. That one comes from the equation given, and then the next slope is what I'm using for my new equation that I'm looking for. Even if it was parallel, I still like to use the parallel symbol, which is like these 2 forward slashes, to imply this is the slope I'm using for my new line. Even though they're exactly the same, I like to always distinguish the difference. So that means I can now plug into my point slope form, which is y minus y sub 1, which our y value is negative 2. So once again, watch out for that negative. There's negatives in the formula, and there's negatives in our ordered pair. Our slope is 3. Then it's x minus, and our x value is 4. Now it does say to write it in slope-intercept form and graph it. I won't ask you to graph it. We have other problems that we graph plenty of times, so I probably won't worry about graphing all of them. So that becomes positive 2. But we do want to write it in slope-intercept form, meaning isolate your y value just like what we did here. So that's 3x minus 12. And then I add 2 on both sides to isolate my y value. Y is equal to 3x minus 10. And that is the equation that is perpendicular to this line, and it passes through this point. Now, here's an example where we talk about being parallel. So that means the line I'm looking for has to have the exact same slope. But if you recognize, look at the line that is given here, right? We're given when x is equal to 4 or just to any constant, we're talking about a vertical line, right? So think about this. If I have a vertical line and I'm trying to find an equation that's parallel, so meaning that they don't intersect, that's just going to be a line that's immediately next to it, right? Either on the right or on the left. So that means I need another vertical line, so that's the equation. The equation we're looking for is a line that is vertical, right? And we got that through sort of our intuition. Now, if it had said perpendicular, well, once again, if this line is vertical, remember, perpendicular means that you intersect at a perfectly 90-degree angle. If this is perfectly vertical, the only thing that would intersect it at a perfect 90-degree angle would be a horizontal line, which we know the equation of all horizontal line is when y is equal to a constant, right? So that means I am just looking for x, meaning I'm just looking at the x coordinate. So that means my equation is x equals 0.372. So I'm looking for another vertical line that intersects this point. This is literally x, and that's y. I want to know what x is. Well, the ordered pair is telling me what x is. And again, these were the examples that we did. And again, there's ways to ask this question dealing with horizontal and vertical, right? Because I could easily just put 2 here, 2 here. And when you do the slope formula, the 2 and 2 will give you 0 in the denominator, meaning that your slope will be undefined, meaning you're dealing with a vertical line, right? Or I could have made this be -1, and then -1 minus -1 will end up giving you 0, making the whole fraction 0, meaning that you have a slope of 0, meaning that you're dealing with a horizontal line, right? So all these ways we can ask the same question. Here, right, I could have also said y is equal to 4. So if I'm looking for a line parallel to a horizontal line, I would need another horizontal line, right? So there's all these ways I can ask these questions, right? But you just need to remember the core concepts, right? Which is, this is what horizontal lines do, vertical lines. And then there's my 3 cases. This is the formula that I use. And these are my other 2 formulas, right? Slope-intercept form, slope formula, point-slope form. Again, there's a lot of these. I'll probably ask like 1 or 2 tops, right? Because the final is everything, so I can't put in all these different examples of these. So it'll probably only be like 1 of these, 2 at most. And then, once again, our transformations, right? We started transformations early on. And I just kept going for them again and again, because I know they can get confusing. And I knew we were going to use them in all the way up to even exponentials and logarithms. Even some of those circles, I said how you can use a transformation to move the center around, right? So that's why I wanted to start early with looking at transformations, which now hopefully we're a little more dialed in, right? The square tells me that I'm dealing with a parabola, right? And don't forget, the nice thing about some of these, for a lot of these, is that they share this 0, 0 point and this 1, 1 point. And a lot of them share that, right? So x squared shares it, x cubed shares it, cube root of x shares it, square root of x shares it, absolute value of x shares it. What else did we do? Technically, y equals x has it as well. But in terms of all these, they all share 0, 0, 1, 1, right, as points. So they're good to use. As for the exponential, remember the exponentials, they all have that horizontal asymptote and that point 0, 1. This is for exponentials. And then logarithms, right? Logarithms share that horizontal asymptote and that 1, 0 point, right? And exponentials, either if it's bigger than 1, goes this way. So it's when the base is bigger than 1, not 0. Oops. So when it's bigger than 1, if it's in between 0 and 1, meaning if it's a fraction, they look like this, right? So it goes the other way. And for logarithms, we mainly dealt when the base was bigger than 1, they do this, right? All right, it's for the logarithm. So again, things to remember from each one of these. Now, for bigger polynomials, obviously we have our P over Q, or our factoring, end behavior. Rational functions, we need our vertical asymptotes, horizontal asymptotes, and so on, right? But these, we could have used transformations to graph all these functions. Which here, right, we start with the inside. This tells me to move the graph over 3 to the left, so 1, 2, 3. So I'd move this point 3 times, and then this point moves 3 times. I would copy the graph. And it's just moving over 1, 2, 3. And don't forget this negative outside, those are reflection on the x-axis. So it looks like this. Again, it's not perfect. So I'll try to highlight them. So the square gave us the parabola. This moved it. This reflected it. And that 3 is going to move it up. So it's going to go. So again, a lot of these points, you can keep mirroring them. Right? The 0 stayed here, but this point reflected down. But now it's all moving up 1, 2, 3. So going up to here. And then the other point's moving up 3 as well. So it's going to be up here. And we're going to have another one right here. And it's going to be the exact same graph. We're just moving it up 1, 2, 3. And let's change the color to purple. But again, moved, reflected, 1, 2, 3. Again, I know this one's pretty big here, but just imagine that's what happened. Sorry, I changed the color of everything, then it all like, what in the world? Oh, why is it all joined together? It's weird. What in the world? Huh. It's copying everything. I'm just gonna do it by hand then. I don't know why it's doing that. But here we go. There's our graph, moved up by 3. And it doesn't have to be perfect, but at least we can move those points around. So, and here we go, absolute value. Same exact thing, right? Here, here. They share those points again. Remember what I said? 1, 1, 0, 0. Here and here. And it's just that slant, right? That V. That -3 does opposite of what you think. Normally we'd look for if there's anything multiplying, which there isn't. And then we move to the constant. That moves it to the right by 3. So this point's going to be here. This point's going to be over here. And then we have the same exact graph. Absolute value. And then there's nothing multiplying outside. And then this brings it down 4. 1, 2, 3, 4. So this point is going to be here at 4. The next point is right next to it. Because look, I'm just going down 1, 2, 3, 4. 1, 2, 3, 4. Same points, same graph. Oops. Here, here. And there it is. Ta-da. Now again, we've had a little bit more added on, right? Because we do have the reflection inside now and the stretching and shrinking, but it's still the same concept, right? It's just here we did it. We started doing them with functions, but now we're able to do them with exponential, logarithm, square root, cube root. It's all these are the same. Honestly, like I can easily change this to, I can write it as -4 plus cube root of x minus 3. And in terms of these points, 0, 0, 1, 1, they're all in the same location. The only thing that will change is, since it's a cube root, I know the cube root looks like this. And then it would move 3 to the right, and it'll look like this. And then it moves 4 down, it'll look like that. Right? I could even make it a square root. So look here, here, and there. All the exact same things. I can make it a parabola. Or I can make it an x cubed, which will look like this. Here. And because they share those points, you can literally make each one of these graphs through these 2 points. You just have to remember what the graph looks like, right? Like this is a parabola. What in the world? Parabola. This one makes that S shape, backwards S. This makes that other loop. This makes that curve. This makes a V. Right? So you just have to remember what each one of these shapes does. But that's good for now.